Welcome back to this morning session. And we are happy to welcome Sarkis from Worcester Polytechnic Institute, speaking on discretization reduction for use problems with recurrent coefficient. Thank you very much.
Okay, thank you very much for the invitation, Ricardo, that made the organization, all the local people. So before I talk about Carlos a little bit, so I'm just going to show this first page here. So this is, in fact, it's a very interesting work because it combines two people of different fields. Alexandre, so he's from LNCC, so he's like a hardcore finite element. Okay, and me, I'm a hardcore domain decomposition. So if you ask what's the difference between domain decomposition and finite element, so finite element, you want to approximate an operator. Domain decomposition, you want to find an operator that's equivalent to the operator that you want to invert. So it's like you're going to replace A inverse by another matrix where they are equivalent. So this is bounded by C times that, bounded below by C tilde. So that's the difference. One you're more interested in spectrum, the other one you're more interested on approximation, okay? So basically you combine those ideas to try to solve a very difficult problem. The difficulty here is the PDE has coefficients that has jumps. Okay, so in general, you have to require regularity of the solution, but you don't have regularity of the solution. So without the regularity of the solution, how can you get a good approximation? So for this talk, there will be absolutely no regularity assumption. Okay, that looks something impossible for the people that do finite element. Okay? Oh, here. So, oops. So normally I don't take pictures. Carlos also doesn't. So I found this in the internet. Okay, so the reason that I'm showing this picture because there are two people here that both are very important in my life, Dan and Carlos. Okay, so let me explain how I start to work with Carlos. Okay, so basically my background was engineering. Okay, so I did aerospace engineering in ITA, it's some technology institute here. Then I did another specialization in petroleum engineering. And then I started working offshore. Okay, so you go there in the deep sea, work 15 days, and then come back, you stay 15 days without doing anything. So that's what it disturbed me most, is like, what I'm going to do in these 15 days here, right? So I started looking for some university here, and then I saw a very beautiful flyer written by Dan. So there is this group, Dan, PJ, Patino, Flavio, so those, and then I decided to give up offshore, be an engineer. So basically I go there, I'm the only engineer, you know, be a chief of 100 people, technicians. So somehow I didn't like this kind of environmental. Okay, so I found this flyer, I went to the PUC, and then I started doing a master degree. Okay, so my salary was multiplied by 0.05, something like this. Okay, so, and basically that's how I started doing my master degree. So, and then I started doing courses like Lucinha, Carlos especially, because I took linear algebra with Carlos, linear algebra 2. Okay, and eventually Dan moved to PUC. Okay, so I was supposed to work with him, but he moved to PUC. And then, since I already have 2 courses with Carlos, and everybody knows Carlos is very, you know, friendly, happy, smart, very smart. So, in fact, I consider Carlos as a genius. Okay, so maybe the people don't know, but Carlos, besides being a very good mathematician, he also is a good musician. Okay, so And that's something that you have in common. I also like music. And then I started with Carlos, did a thesis with him.
What? Give us catching on the line.
Exactly, what he's not here. So you complexify, right? That's how I forget. You complexify, and then you do Fredholm, things like this. So basically, the problem was like this: you send a wave with a frequency, and then you want to see what happens with this wave. So it's going to propagate, and it's going to reflect. So you do this for all the frequencies. Okay, so take this object with all reflection or transmission, and from that one, you try to recover a coefficient that is from the Schrödinger equation, right? The second derivative plus Vx times Vu. Okay, so the goal is to find that coefficient. So this was my thesis with Carlos. It was very difficult for me at that time, okay, because it requires a lot of functionalities. Etc. Okay, and then I moved to current. So maybe I'm the only student of yours that went to current. Mario, claro, of course. Yeah. So Mario was my colleague, and then Juliana also. Okay. So I met Juliana finally this conference. And then I think I was very lucky because I think when I moved to current, I moved at the right time in the sense of courses, right? So, example, I took a sequence of courses with Nirenberg, like 6. So, I have a course with Persdave in analysis. I have a course with McKean in complex analysis. I have a linear algebra with Carlos, so it was easy to pass, not easy, but to pass the preliminary exams with all these top teachers. Okay, so Lax, Garabedian is amazing also. It's funny because he takes his little book, this size, he opens, close, and then his proofs in fluid dynamics is like one line. So it's like very intuitive proofs, okay? And then Weitzner, so I think this board here, you'd meet not enough for his formulas. So and all the numerical analysis people, like Olaf Wiedeland, Greengard, Michael Overton, Goodman, Malat. Okay, so in PG also, it's like I started doing harmonization. That was, in fact, I started working at the beginning with Bob Cole, and then I moved to linear algebra. Domain decomposition. Okay, so that was a very difficult moment in my life also to change a divisor because analysis is not exactly what I like. Okay, so I prefer linear algebra, finite element, these kind of things. And then, so that's the second moment that I met Carlos and I started discussing this. And then he suggests some people like Demo, James, but he was not at current. So then I took Olaf because besides this linear algebra, the numerical linear algebra, also there is a connection with PDEs. Okay, so that's also more or less the stories. So I'm very grateful to Carlos because he changed my life. I was this engineering, don't know what to do. And then Carlos somehow introduced a path for me. Okay, so I'm very grateful. Thank you very much. Of course, I'm never going to forget this. Okay. All right. So let's continue here. So I'm going to introduce the problem. It's like a transmission problem. And I try to do something that sometimes the people call model reduction. I don't call model reduction because basically I'm not changing the model. Okay, so basically what I'm doing is to try to find a good subspace so that I solve the problem in that subspace. Okay, so so what's the picture is doing here? Okay, all right. So the problem of interest is this one here. So basically, classical, so if A is 1 is the Laplacian. So the difficulty here is that A can have big jumps. In one place it's 10 to the power 6, The other one could be 10 to the minus 6, could be random. So the question is how to get a good solution without assuming any regularity. So the only thing I'm going to assume is the functions in H1, okay? By now, I'm going to assume that the lower bound of this coefficient is 1. Okay, so this is the maximum, so this could be 10 to the power 6, this is 1. So that's the classical norms that are used, the L2, the energy norm. Okay, so I solve this problem in this space. So I'm going to go to talk U star as the exact solution. Okay, the discrete solution, I'm going to call U. I don't like to carry little h. So remember that U is going to be the discrete solution that depends on little h. Okay, but it's going to be the same problem. I have to choose a space that is contained in H1, so you call conforming finite elements. Okay, so there are other methods that you don't have this assumption here. So I'm going to use finite element. You have many options how to describe this space here. So I'm going to use conforming P1. Okay, so what is conforming P1? I don't know. Conforming P1 basically is like this. Let's think 1D. Okay, suppose you have a line here. Suppose those are the nodes. Okay. And then your problem is like you define values here. So think this is the y value. So you do straight lines. Okay, very easy. Okay. And this straight line is very interesting because, example, if I ask you, give this value here and this value here, and I ask you to solve the Laplacian here, it's going to be the linear function. Okay, so very easy in 1D. Okay, if I have a coefficient here in the middle, example, the coefficient here is 2. So basically, you can compute also because you have to have continuity, but also the continuity of flux is going to tell you that the slope of this has to be twice as the slope of this. So imagine that if this coefficient is 10 to the power 6, basically it's going to be like this, almost a constant, and going down. Okay, so it's very easy to solve this problem in 1D. In fact, there are very interesting results like if you solve this problem at the nodes, you get the exact solution. This happens just in 1D, okay? Not in 2D. So then I'm going to, so I have a mesh here. In this case, those are the little h, okay? But I'm going to do in this talk in 2D, okay? Not 1D, because 1D there is nothing to do. And then I introduce another triangulation. So imagine that this is like 1 divided by a million. So little h is 1 divided by a million. And then I do a coarse triangulation, let's say 1,000. Okay, so each 1,000 here, I have a lot of 1,000 fine one. Okay? So I have two triangulations, the little one and the capital one. Okay? Yes. So the only assumption that I'm going to do here in this talk is that assumption here. I'm going to assume that I'm going to choose a mesh that is very fine so that I have a good accuracy for U. So that somehow is a regularity assumption. Okay? So the goal here is basically like this. I have this very fine mesh, but now what I want is to compute functions on the coarse mesh, but now it's not going to be equal to the linear one or this thing here. It's going to be something very special, okay? Especially in 2D. So let's go to 2D because I see that the people here are not so familiar with finite elements. So in 2D, basically what you're going to do is to take this domain and triangulate. So you fill this domain with triangles, okay? I remember once that Carlos asked me, why triangles? Right? I remember that he asked me this question. So there are two, at least I see two important reasons for this. So example now that you have like a triangle here. Okay, so think this is a triangle. Okay, start like this.
The microphone is a triangle.
So nodes, node and node. So you have a triangle here.
Oh.
Okay. So you have, if you have a value here, and a value here, suppose 0. Yeah. So how you find a function that passes for these 3 points? A linear. So linear is linear, right? So it's better than some quadratic things like this. Sometimes when you do elasticity, sometimes you need to invert this matrix. If it's linear, it's very easy. If it's not linear, so that's one reason is linear, okay? 2, okay. In 3 is a tetrahedron, so it's going to pass in 4 points a plane.
But you are in dimension 2, so
2 is a triangle, okay? Now I ask the following question. Before I ask you, suppose the coefficient is 1, Laplacian, okay? I asked before, like, give a value here, what's the function that has the minimum energy? It's the one that solves Laplace of u equals 0 in the interior. So it's going to be the linear one. Suppose now I ask the following question. I give a value here, and a value here. What's the function that gives you the minimum energy? Okay, so the problem here is like this. You don't know the value here. If you knew the value here, it's easy. It's like you solve a Laplace of u inside. You do some harmonic extension. But the problem that you don't have here. So there are 2 possibilities here. One is to make it linear here. Suppose you have another node here. So you have 2 triangles doing this. Okay, and the other node is here. So you can one way to do is to pass a plane here, a plane here. The good news is that because this is a plane that traces a line, it's a plane that traces a line, and they match. So that's another reason to use a triangle. It's easy to do this. However, this is not the minimum energy function using the union of these 2 triangles. Why not? Because you see here it does this and does this. So you see that the normal derivative doesn't match. So if I take a little circle, take the Dirichlet here of this function, do harmonic extension here like Perron technique, you are going to see that the energy is going to go down. Okay, so you see that if you have 2 triangles, it's not so simple to find the minimum energy. Okay, another possible way to do is like this. I have this value, I have this value, I have this value, but on the edge of this triangle, I make Neumann boundary condition and solve. So this is going to give even a smaller energy because you have more degrees of freedom. Your space of minimization is larger because I'm not imposing Dirichlet. I'm imposing Neumann. Neumann is a free value that you can choose. So the problem with technique is like that. If you do this here, if I do this here, they are not going to match here. So there will be a jump. Okay? So basically what I'm telling to you is like this. Well, to do this thing here, basically I have to solve all these problems together. I have to find a function that is harmonic also on the intersection of these 2 triangles. Okay? For us, it's going to be like, it's not just 2 triangles. It's going to be many triangles. So if I put 1 here, 0, 0, 0, 0, 0, so this function is going to be global. Okay, so that's the catch here about the final term that I'm going to introduce. Our base functions are not local, it's global. Okay, so one of the problems about base functions that are global is that when you insert here, all these base functions are base, so you generate this function here, you are going to see that this matrix is going to be dense. So you don't want dense matrices, okay? So you like sparse matrices. So you have to do something. So what is something that you have to do? You have to guarantee that this harmonic extension globally decays exponentially. If it decays exponentially, I go there, like take 3 triangles and chop. And then I have a local basis. Okay, so that's the question related to André when he asked a question about when you do this conforming, why is local. Okay, so you have to guarantee somehow that you have exponential decay so that things looks local, okay? All right, so let's keep going here. So basically, I want to find this function that basically I give values at all the nodes, okay, extend harmonically everywhere. Not just here, but also on the edge, okay? So this is, if you take the span of all these bases, I'm going to call this multiscaling, okay? So basically we have few degrees of freedom, but the function is defined on the fine mesh, okay? Just like why the people start doing this? In fact, this kind of method started in Navier-Stokes. So what the people, like Tom Hughes, so they call multiscale finite elements. So he's introduced this for the Navier-Stokes. So why did he do this? Because in Navier-Stokes, if we have a very large Reynolds number, you're going to see that the mesh has to be very fine near the boundary to resolve the boundary layer. So the question is, can you do without that resolution? And they used to use some technique like this. You define in certain points, and then here, instead of doing linear, you take function that is defined by the PD. So you do some harmonic extension in the Navier-Stokes sense. They all seen, so they linearize Navier-Stokes. So, but our problem is this one here. So I replace this space by that, okay? And then I solve this problem. So basically, we can show that how to design this function here so that I have this kind of approximation, where delta, I choose the delta I want. Could be capital H, could be even smaller if you want. Okay, so that's a very interesting technique that you tell what is delta, and then I'm going to tell you what's going to be our multiscale finite element, so that you have this kind of a priori error estimates, okay? Of course, you can imagine that if delta becomes smaller, the dimension of this problem here is going to enlarge. It's going to be larger and larger and larger, okay? So the important thing here is that I'm going to get estimates like this, where this coefficient here independence of A, independence of domain omega, independence of F, okay, independence of all these parameters here. Okay, so of course, this space here is going to depend on this. Okay, not F, but on A, all right? So the question is how to design this space, this multiscaling space, that's going to give an approximation like this, okay? So let me give you one theorem, okay, because the other ones are very long, okay? And this is very short. So in finite element, there is this thing that's called the Ritz projection, or Ritz-Poincaré projection. Basically, the idea of the finite element is like this. You take the exact solution, the discrete, and you project in the space VMS on the A norm. That's what finite element is. You choose a subspace and you project. How you do this in terms of bilinear form? So first of all, see that if I want to compute this, see that U minus UMS, because you're projecting orthogonally, is going to be orthogonal to this one. So I know that's going to be 0, because it's a projection. Okay? Now, if you can put UMS also if you want, okay? Now, if I put just this part here, without this one, because I know that is 0 from here, so you get this one here, because this is the solution and this is the test function. I'm assuming that A is symmetric here, so you don't need to talk with that joint problem. And is equal to this one, that's the problem. So basically, if you want to have an estimate like this, I have to do some sort of Poincaré inequality here, so L2 and this one. So to have that theorem that I asked you that's what I want to get, I need from here to have an approximation L2, some sort of local Poincaré inequality. You try to bound the L2, but the H1, okay? But I want to have delta here, all right? So another way to think is like this. You have a function here, okay? And then you project somehow. So I see that this distance here is going to be proportional to delta, okay? So somehow locally, you know that this function minus that one, they have 0 average. So that's how you apply Poincaré, okay? So basically, that's what you want to get. So basically, this space that I'm trying to design should have two properties. One is that approximation here, okay? The second one, I would like to show that things decay exponentially, my basis. Okay, so these two properties, that is important. So I want the exponential decay because I want my matrix to be sparse, okay? So let's go to the first one, first method. So this is just like a warm-up, okay? So there is this, that's how things start working with me and Alexandre, because we try to combine finite elements, LOD, it's called local orthogonal decomposition, with BDCC, that is a domain decomposition method, a balancing domain decomposition with constraints, okay? In fact, there are very similarities between those two. So let's start with how to do this. So as I mentioned before, this kind of method starts with Tom Hughes. He used this to decrease the dimension of solving Navier-Stokes equation. Okay, I'm doing Laplacian elliptic problem, but you can do also for Helmholtz. Okay, one of the problems with Helmholtz is that if you have a very high frequency, you're going to, and you try to use piecewise linear function, you're going to see that the mesh has to be proportional to 1 over k squared. So it's going to be too fine, okay? And it's impossible, okay? So if you try to do very high frequency, okay? So this method that's called the LOD, this method that somehow was introduced by Hughes and analyzed by this paper here, okay? Allows you also for Helmholtz to avoid this, they call the pollution effect, these kind of things. So I'm discussing about the elliptic, but you can extend this to Helmholtz, indefinite. I'm talking about the indefinite Helmholtz, the one that comes from wave equation. Also for the linearized Navier-Stokes, okay? To make simpler here, I'm going to assume that my coefficient that I have here, this coefficient here is between 1 and 10 to the power 6, okay? You can do this just by normalizing the equation by the smallest a that you have. But I'm going to do more general later than this, okay? So these people here, oops. Very interesting paper, okay? So if you want to start doing these fields, read this paper here. Took like 2 months to read. Okay. It's a beautiful paper, okay? Because one of the difficulties is how to show that function decays exponentially, okay? So there is this Cacciapoli inequality that basically is to do the reverse. For example, you know how to bound the L2 by the H1. That is easy, okay? Because you use the Poincare inequality, so you can bound the L2 by the H1, and then the problem is the opposite. Can you bound the H1 by the, it looks tricky. The answer is obviously not, because how are you going to bound the H1 by the L2? However, if you know that this function is harmonic, you can. Okay, so you impose some regularity, this kind of thing. So there is this very important inequality that the people use, this inverse Poincare inequality that in this paper here. So they show that things decay exponentially. If the jump of the coefficient is small, 2, 3, I'm interesting, 1 million, okay? So that's our contribution here. So I'm going to take this interesting example. So imagine here that I have capital H, so it's a coarse mesh. In this case, it's 8 by 8. And I have a very fine mesh, this one here. But here, this is the coefficient I'm going to choose. 1 in the white region, here. And here, I'm going to choose 100. Okay? All right. And suppose I ask the following question. I want to build a basis. Suppose I put 1 here and 0 in the other ones. Okay, the question. And then you do harmonic extension, harmonic in the sense of coefficients, and I ask you, what's going to happen with this function? Is it going to decay exponentially or not? Okay? If the coefficient is 1, it's like this. You can imagine that you have a tent, and then you put a pole here equal 1, and then you start gluing. Many points 0, 0, 0. Okay? We are going to see that this function is going to decay exponentially very fast. If the coefficient is 1. If it's not 1, so let me show more or less what's going to happen. I put 1 here. And you see these little things here is because I impose 0. So it decays exponentially very fast. Okay, so if I put 1 in one vertex and 0 in the other. However, if you try to do this kind of coefficient, you're going to get this kind of extension. So obviously it's not going to decay exponentially, so you cannot chop.
What is that?
So think like that. This is 1 here.
Yeah, what is it like? Is it
So if you think like this locally, this looks like the fundamental solution, the green function. So this is the discrete green function in this case here. So you might ask, why it doesn't decay exponentially here? The reason is, let's go to our picture. The reason is 1 here, right? 1 here, and 0 here. So what's going to happen, because you want a small energy, this function here, you cannot go to 0. Otherwise, you're going to have a gradient, and it's going to give big energy. So the function try to be constant where the coefficient is large. So in all this connected region here, the coefficient try to not decrease to 0 fast. Of course, from here to this point here is going to decrease fast. But here, the coefficient is 1. So it's not so bad. So the problem is like this. If you do coefficients 1 and 2, you're going to get that one that I showed to you. It decays exponentially, but if your coefficients start having big coefficient in certain places, it's not going to decay exponentially. Since it's not going to decay exponentially, so what's going to happen is that you cannot chop. So your matrix has to be sparse all the way, okay? But let's go back here to here. So what I'm going to do, now comes some sort of domain decomposition. So basically, I have my mesh, like here. This is my coarse mesh, my fine mesh, okay? I'm going to divide, I'm going to classify nodes here. I'm going to call nodes vertices, edge nodes, and interior nodes. If you are in 3D, you're going to have vertices, edges, faces, interior. Okay, so I'm going to classify those nodes as, so omega I is the big squares. Okay, and then I look the boundary of each big square, I call gamma I, so the boundary of each big square, not touching the boundary. Okay, and then gamma is the union of all these boundaries. So this is the interface. So it's all this black. There are many nodes here, so this is what is gamma. Okay, all this thing here. Okay, so you're going to see that I have vertices, edges nodes, and interior nodes. Okay. So I'm going to separate in 2 groups. One, the vertices, and the other one, the rest. So it's like this. I separate those nodes, but the other ones that are in the interior on the edges, I'm going to call R of remaining, resto. Okay, so and how? So the question now is linear algebra. How, given values at the vertices, and I say that is harmonic everywhere, so how you do this numerically? It's very easy, in fact. You create your matrices, your matrix A, define mesh, okay, so you have the vertices and the rest, the remainder. So that's the system that you want to solve. So basically, if you want to do this, so basically what I need to do is to go example, I can put example 1, 0, 0, 0, 0, 0. So basically I'm saying that this one is 1 in one point and 0, 0 on the rest, on the vertices. And the other one is my unknown. Okay, so basically I'm going to see that given this one, and you use this equation here, you're going to see that since I know the values is 1 in one vertex and 0 in the other ones, I can throw this to the right-hand side, and then basically I have to solve this problem. ARR is equal to something there. Okay? The problem with this that is right here is that this is too big to invert. It's almost the whole thing except the vertices. Okay, so the question now is, what can you do here? So those basically like that, you go to some vertex xi, you put 1 there. For the other vertices, you put 0. And then you solve this problem here, put delta xi here, you find and plug here. So that's going to be my basis. Okay, so numeric is very easy to do. So let's go to the numeric experiments that I already showed to you. So you divide in 8 subdomains. The fine mesh is going to be divided by 8 again. I'm going to consider 2 cases. One you have low contrast, and the other one very large contrast. So how the solution looks like. So this is low contrast, decay exponentially, so you can cut, and the other one doesn't. Okay, so what to do? I'm going to do something that now when I look at the decay, it's going to decay exponentially. See, can you see that it's decay exponentially? Look here, this is the log normal. Okay, so I'm going to do something that if I plot in the log, it's going to decay exponentially. So you see that it's very fast. In fact, numerically, you're going to see that I just need like, in 3 elements, it's already almost 0. So I can cut there. So my base is going to take like 1 or 2 or 3 elements around. So it's very sparse at the end. Okay. I'm not going to talk much about theory, about the exponential decay, but how you prove exponential decay. Basically, you try to compute the energy here, and you want to show that the energy here is bound by the energy here, times a constant that is smaller than 1. So if you do this many times, decrease. Anyway, I'm not going to talk about this, but what's important is like that when you try to do the analysis, you're going to see that the energy of the one that is outside layer until the end with the other one, okay, here. You are going to have this constant here somehow. And the problem with this alpha is going to depend on the contrast. So this number here is going to be very, very close to 1 if alpha is 1,000,000, example. So it's going to take forever to decay. Okay? So I'm not going to use, now I'm going to do more than that, just vertices, okay? So that's where domain decomposition comes. There are many methods here. So this talks related to this paper here that you just finished. It's in SciM, numerical analysis. It's there if you're interested. Okay. And you are going to get estimate like that. So see how beautiful this estimate is. This is when you solve the problem without cutting the function. Okay, so you work with this global one. Okay. And this is when you cut. Okay, don't look for this one. Just look at this one. So the constant that I get here, and that constant C, delta, that constant is, so by the way, alpha, you're going to see later, that's like 1.3, 1.5. So I'm going to see that this constant is like 5. It's not something that depends on the coefficient. So it's 3 because you're using triangles. If the element is quadrilateral, it will be 4, things like this. So it's very sharp somehow, because sometimes when you see people doing this for overlapping, you're not doing overlap, you're going to see that this constant is very messy. Because you have overlap, you have to count, use some function from here, some function from here. So this constant becomes very ugly, okay? In fact, they cannot do, our estimate here is going to be better than theirs, okay? So let's look this part here, okay? So L is how many layers you're going to cut. Suppose I cut in the third one, L is equal to 3, okay? This is a simple constant or universal. Don't worry about this. This alpha is going to be 1.3, 1.5. So this is fine. So let's look at this thing here. So the interesting thing about it is this log here. So this is the Poincare inequality that you have globally is order of 1. Okay. So basically I have this log of 1 over delta. Okay. So basically I'm going to see that if I want delta capital H, example, you see that the number of layers that I need is log of capital H. Example, if capital H is 64, so it's going to be log of 64. Okay, so I'm going to need log of the accuracy that you want, delta. And this is the part that's going to save us, so this is going to dominate that one. If I can show that this alpha here is nice. So you see that as I increase L, this is going to dominate this one here. Okay, and then decay exponentially. All right, so if I choose L to be log of 1 over delta, you're going to see that this is going to be small. Okay, large, okay, because I have this negative here. The other works, they don't have this constant here that is order of 1. They have something that is the maximum. That is horrible. Okay, so all these papers that were done before me and Alexandre, somehow they cannot prove exponential decay in the proper way because they are doing overlap. Overlap is much more complicated. So let me see what I'm going to do here. So basically the idea now is like this. Okay, instead of giving the value here, and make harmonic everywhere, I'm going to say, okay, in this edge here, I'm going to introduce some functions. So I'm going to enhance my degrees of freedom, not just the value of here, but some function that is going to be 0 here, some bubble function, okay? I'm going to enhance to these 2 degrees of freedom, okay? So the question is, which function am I going to choose? Right, so you can choose the classical bubble, like x times 1 minus x, things like this, that you're going to get a bubble, but because you have coefficient, that bubble is not good, okay? Example, if you have a coefficient here, example, you like this function to maybe do something like here, and then constant, and go here. So the kind of math that you want to do here is, you like to be like, you just press the button, and you get the answer, okay? So you cannot try to figure out, given a coefficient, what is going to be the function. Okay, that's the good thing about linear algebra. You just solve and you get the answer. Okay, so the question is solve what? So basically what we are going to do like this, I'm going to introduce functions here, so the edge, let's say introduce 1. So when I say that is harmonic here, is harmonic up to that constant. Okay, so I'm not going to say that the Laplace of u is going to be 0 here, but in all the nodes, but I'm going to say that it's harmonic in a subspace of the nodes that are here. Okay, so basically what I'm going to do is like this. Instead of doing the harmonic extension everywhere, I'm going to add another function that we call primal. Okay, so this is primal. Whatever is left out, the orthogonal of the VH compared to these functions here, is going to be the function that I'm going to do as a test function of the harmonic extension, okay? Now comes the domain decomposition part, because we do this in domain decomposition, a different way you have to modify. So the question is how to find a good function here. 0 is going to be 0 because this node here is already on the space that we start with. Okay, now I'm going to try to introduce functions that is 0 here and something here. Here is going to be always harmonic. I'm going to create 2 operators. The first operator that's very important is the following. I give the Dirichlet here. I give the Dirichlet 0 here, 0 here, 0 here, 0 here. I extend here, and see the jump of the normal derivative. So I'm going to call this map Dirichlet-Neumann. Okay, so I call this S. Okay, and then I'm going to introduce another operator that instead of putting 0 here, I'm going to consider Neumann. Okay, so he's going to be Neumann, and here's Dirichlet. So you solve, see what's the normal derivative here, and see the jump. So you create this Steklov-Poincaré operator that go from the Dirichlet to Neumann. Okay, so I have these 2 operators. Guess what I'm going to do with these 2 operators? I'm going to solve a generalized eigenvalue problem. Okay, and using this eigenvalue problem, I'm going to pick the first eigenvalues and eigenfunctions, And those will be the functions that I'm going to introduce on the edges. Okay? So how many minutes do I have?
Little more than 10 minutes.
10 minutes, okay. Okay. So, and that's exactly what I'm going to do. So this is the PUC-Rio operator that I mentioned to you. You give values at the edge. Dirichlet 0, Dirichlet 0, Dirichlet 0. Solve and see what's going to be the jump, okay? The Neumann one that I put Neumann here, 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 is what I call S tilde. Okay? In fact, I can get S tilde from that one by doing the Schur complement of the Schur complement. Okay, so there are many tricks that you can do to avoid some calculations. Okay, so I create these two matrices that is called the SI, that's the Dirichlet, 0 here, and the tilde Neumann 0 here. I'm going to solve the generalized eigenvalue problem. So this means that from one side is the Neumann, so I sum the S. So the jump is the same thing as you extend harmonic here and see what's the slope. So this is going to be the first one. Okay, in the domain omega j, you solve here, see the Neumann. When you add, basically you compute the jump. Okay, there is some normal that's going to make the minus. Okay, and the other one is going to be the Dirichlet. Okay, and then you solve this, you're going to get eigenvalues and eigenfunctions. Select some that is, the ones that are more concerned are the ones that are, the alpha is large, when these two matrices are very different. Okay, so basically what I like to do is to select the eigenfunctions that the associated eigenvalues are large. Those are the functions that I'm going to put together with this one. Okay, the rest is together with the interior and the edges that I didn't select. So now our primal is going to be vertices and those eigenfunctions that I select. The remainder now is going to be the interior nodes and the eigenfunction that I didn't select. I just like to mention that I don't need to solve the eigenvalue problem, find all the eigenvectors. I just need to find the other ones, the few ones. So in some sense, the eigenvalue problem that you have to solve is not to find all the eigenvalues, just the eigenvalues that are bigger than 1.5. That's much cheaper, okay? So I do this, and let's see what happens, okay, in terms of numerics. First, let's see how the eigenvalues looks like. First, we're going to do is like that. Let's consider the coefficient 1 everywhere. So let's see how the eigenvalue looks like. So I'm going to see that if the local mesh is 8, so you divide the subdomains or the macro elements by 8. So I'm going to see that decays to 1 very fast. So if you select like 1.5, basically I just select 2. It's not many. Except this one, there are 32 here, 32 nodes. If I select all the eigenvalues that is larger than 1.5, 2. It's not many. Okay? This is coefficient 1. Now what is interesting like that, if you have a channel here, coefficient, that here is 1 and here let's say 1,000,000, you ask how many eigenvalues do you need? So the answer is going to be the number of channels that are crossing this line here. So somehow you know more or less how many there are if you know how many channels are crossing that edge, okay? But you can do this systematically. You don't need to look, this kind of thing. You just go, take 1.5, select all the eigenvalues that are smaller than 1.5. In this case, if you're dividing 8, it's 2, 2, and 2. Okay? So let's solve the problem again. But now adding the edge functions. Okay? So the same, you have 8 subdomains, divide each one by 8, so I'm going to try 100 here. Okay, so if you look this mesh, there will be 112 edges. Example, if I select one eigenvalue for each edge, so basically you're increasing the dimension of the problem is going to be the number of vertices plus the number of edges if you select one. So it's very small, right? So, and I select in this case, I'm going to choose 1.3, the alpha. So basically, this is going to be the number of prime if I select one eigenfunction per edge, and this is what is left out. Okay, so you see that this is smaller than this. This is for 8 by 8. Of course, if you see 32 by 32, the difference between this and that is going to be much larger. Decay exponentially here. So I took the vertex, one here, 0, 0, 0. Also, my harmonic extension here is going to be orthogonal to those edges that I select. So now you're putting more pressure. It's like before I pin here, 0, 0, 0, right? So we saw that if the coefficient is big here, this is not going to decay exponentially. But if I make this harmonic extension to be orthogonal to those functions that I select, you're pitching more to make the function to be closer to 0. So decay exponentially. Let's skip this. So let's run. So this is going to be our exact solution. So let's just go back here. Same problem. So I put, to make a little bit more complicated, instead of select 100 here, I'm going to select 100 times some random number between 0 and 1. Okay, so you might have a very small number there because if your random is 0, 0, 1, things like this. So the coefficient is much complicated than just 100. So this is going to be something between 0 and 100 if I use this distribution here. I do the same thing for f. Instead of taking f equal 1, I also choose some random. And that's how the solution. You see that there is some wiggle here because of the random of A. So let's see how the error looks like. Okay. So I choose alpha equal 1.5, meaning that when I solve the eigenvalues that are selected is going to be all the eigenvalues above 1.5. And you saw that these are, the most of them decrease to 1. Okay. So this is the error if I don't do anything, just use the vertices. So you see that the error of the energy by F is 0.23. And see that the function here is like the top is 0.6. So you're going to see that that's not a good error. Okay. Now when I start choosing delta, as delta gets smaller, the number of eigenfunctions that I'm going to choose in edge is going to get larger. Okay, so basically see how the error is now. Much better. You're talking about factor of, big factor, 50. So if you start decreasing this delta, I'm going to have more eigenvalues, and that's the error. So here I didn't localize yet, okay? But we know that decay exponential, you can prove this. So that's the first indication that if I just use the vertices, bad. Okay, you have to add edges. So this is the number of, so you see, example, if I choose this one, because I have 121, right, edges, so you see that this is like 2 eigenfunctions per edge. Very few. That's the error. In fact, this is the error, okay, it's 10 to the minus 3. That is consistent with those numbers that you saw here. Okay. So this one here is like, what is this? This one, what is this one here? This one is like, instead of I extend globally, I'm just going to extend here, locally. Okay? So you see that this is not enough. You have to have L, the number of layers, to get larger and larger and larger. So you don't get good errors here. they have decreased as before. You increase the number of eigenfunctions. So this is the very interesting table. Now, suppose I take those eigenfunctions that I showed to you in the log plot. Suppose I cut like L. L means the number of layers that you're putting. Suppose I put L equal 1, 2, 3. Of course, if you start cutting 3, 4, 5, it's going to be almost the same because it decays exponentially. So see here that this, if you don't extend at all, just neighbors. So when you start increasing the number of layers, you see that eventually you're going to see here, for example, this one is like 2 layers. So L means 1 layer beyond these 2 triangles here. So you're going to see that you don't need much to have exponential decay. So you see that you can chop the base that you got, like after 1 or 2 elements is going to be enough. You see that it's not going to improve. Okay. Here you see that it's taking more time because I choose alpha to large. Alpha to large means less eigenvalues that I'm going to select. The same, I just choose alpha equal 1.5. So you see that things decay exponentially. So basically, the method that we introduced here was, I assume at the beginning that I have a very fine mesh that solves the problem. That's the only assumption that I do in terms of regularity. I have a very fine mesh. Then do some discretization reduction. So I want to select a dimension that is much smaller than the final one. Okay? And then I show that if you select those base functions in a proper way, you are going to have approximation with the delta that you want. Example, if you decrease delta, the eigenfunction, the number is going to increase, and then you have a better estimate. Okay? So this is the paper that is related to this talk. You have another paper that's now the idea is not to use Dirichlet here, but you give the Neumann data. Okay, so it's like you call the mixed finite element, hybrid finite element. Okay, so basically that's what you have now published. Okay, you've been working in trying to, example, suppose f is not in L2, like a delta function. Okay, so this estimate is not going to give much because this is going to be very large. In this case, rho is equal to 1. Forget about, I didn't want to discuss. Let me talk about this rho. Why is it important? Suppose now I don't assume that the A minimum is 1. Suppose here in the interior I say that A is 10 to the minus 6. So this is a much more difficult problem because it's less elliptic, because the coefficient is going to 0. So if I have to do something extra, okay? So the idea is that I have to be careful about what's the norm that I want to bound, okay? So that's something that I'm trying to do with Madureira. It's not easy, okay? So we don't know the solution yet, how to do. In fact, I learned something very interesting. If you know the answer, don't waste your time to publish a paper. So you always try to write a paper when you don't know the answer yet. Okay, so we are working now on this, me and Alexandre. I can tell you also that you can extend this to Helmholtz because some people have done, not with coefficient, but to avoid this assumption that the mesh has to be small enough compared to the wavelength of the. And finally, I just want to mention that all this started with Navier-Stokes. So I'm not just doing for elliptic. So you can do this for non-symmetric with bounded layer. But there is no analysis yet. There is the method, but given by Tom Hughes. Okay. So anyway, so this I saw that the next talk is going to be about the LOD also, because that's one of the reasons that I chose this talk, because I saw, the next one is going to be LD, so maybe I should talk about LOD. Okay, so I'm going to see that probably the next talk instead of saying that you are going to give the value here, you're going to see that, well, the average of the function in this part here is given. In our case, the value at that point, okay? So that's going to be the difference. And the problem with doing this average here, that when you start doing eigenvalues, this kind of thing, you start overlapping eigenfunctions and becomes messy, okay? So thank you very much for wake up early. Okay.
Thank you very much for the nice talk. Are there any questions, please?
Actually, just a curiosity, why did you take alpha equal to 1.5 and not something else?
Okay, there is always this question. When you work with adaptive, you have to select alpha, okay? So how did you do? First, we did for coefficient 1, okay, Laplacian. And then we saw, okay, for the Laplacian, what's the good alpha? So I showed the table that if you select 2 is fine, okay? When you go to a coefficient that is 100, things like that, so basically you are going to introduce more eigenfunctions with eigenvalues that is larger, like 10, 100. So basically the alpha that we chose was to recover the same results that you get for cos A equal 1, but also you take all the eigenvalues that is above to that one. Because at the beginning you don't know, it should be 3, 1.02. So basically you do Laplacian first just to calibrate. And from there you can take the other one is going to be just worse, okay?
Other questions, please?
I have a very silly question. Once you decide, I love this business that you're using functions out of microphones. Once you decide a choice of Steklov operator, for example, and you look at the generalized eigenvalue problem, right? You find, of course, a collection of eigenvectors. How, quote unquote, universal are such functions? Do they vary substantially from one example to another?
Yes.
They do.
Yes, example, let's see, the fall is like, suppose you have a channel here. So you're going to see the next eigenfunction, maybe is going to be something like this. Here is going to be constant, and then go here. And then you're going to see that there is no more eigenfunction that's going to give alpha big. Now, if you have 2 channels, you are going to see that 1 is not enough. Also, the plateau might be different. It's not going to be any more here, it's going to be here, so the eigenfunction is going to be, example, if you have 1 here, another channel here with large coefficient, you might have something here, and then linear here. Something like the other one is going to be constant here, here, there. But that's not exactly the eigenfunction, because you know that they are orthogonal, things like this, but they are going to be very close to these ones. In fact, that's how you prove using a Courant-Fisher kind of result. You can bound from above and below using this kind of technique by using this function that I just showed to you. If you have like 2 channels, let's see the first one, the second one, and then use Courant-Fisher kind of argument, and then you estimate that there are only 2 bad ones, okay?
Yeah, so you're really giving me the impression that they are almost universal.
That makes a lot of difference. Yes, if the coefficient is 1, you are going to see some little things on the corner, because if you look a function that is something here, but 0 here, so this is like thinking like how to go from h half to h half 0, 0. Okay, so it's like doing eigenfunction, a generalized eigenvalue problem with h half, which h half 0, 0, that is smaller, is by extended by 0. So you see numerically, you are going to see some log of this divided by this. So normally the first 2 is going to be related to those singularities that you have. But it's very weak singularity. Log is not a big deal, but we move, right? It's like, yeah, so, yes.
More questions? Okay, let's thank you.
Thank you.